Hello, everyone. Thank you for joining me today as we continue our conversation on the electronic structure of atoms. We're now going to jump in to talk about how to use those quantum numbers that we introduced in the previous chapter. We're going to talk about how to use those to write the electron configuration for an element. And then we're going to finish the chapter with talking about properties of atoms, specifically periodic trends that can be used to say something about either the electronegativity or the metallic character of an atom. But before we talk about the first topic, electron configurations of atoms, we need to introduce just one more quantum number. If you remember from the previous videos, we introduced 3 quantum numbers that explain an orbital or a region of space where an electron is most likely to be found. Those quantum numbers were the principal quantum number, the angular momentum quantum number or azimuthal quantum number, and the magnetic quantum number. Now we're going to talk about the fourth and final quantum number, which is called the spin quantum number. This quantum number speaks to the direction of the spin that a particular electron has in an atom. And unlike the other quantum numbers that could have various values associated with them, there are only 2 allowed values for the spin quantum number, either +1/2 or -1/2. That sign just denotes the direction of the spin of the electron that is being talked about or discussed. And we symbolize that spin with the direction of an arrow. We're going to talk about more about orbital diagrams, what you see here on the right-hand side of the screen later on in subsequent videos. But when we show electrons in orbitals, we designate the spin by having arrows of opposite direction. Also, an arrow represents an electron. An orbital represents a box. We'll go over this again in another video with orbital diagrams. And the designation of that orbital, of that box, is written below the box. Take-home point from this slide is that we designate spin of an electron by the direction that the arrow that the electron is pointing, either upward or downward. That's the first point. The second point is that when electrons are paired in the same orbital, like here you see that there are 2 electrons in this 1s orbital, you see that they are of opposite spin. That's going to be a rule that you're going to need to use when constructing orbital diagrams later on in this chapter. So that's the second point from this slide. So spin that is designated by that m sub s quantum number, the spin quantum number. That spin we will use with orbital diagrams and in electron configurations, and that spin is an indicator of a material that determines if it has magnetic properties. And so when we talk about material, if it can attract a particular pole of a magnet, we tend to use these 3, or at least I tend to use these terms as synonyms, but they mean 2 very, very different things. So when we talk about something being magnetic, that species can either be diamagnetic or paramagnetic. And those are the 2 we are going to focus on really in this chapter. Ferromagnetic is similar to paramagnetic in that both of those substances have unpaired electrons, but a ferromagnetic substance has a very strong electromagnetic field. Whereas a paramagnetic field, that is a species that has unpaired electrons, and the field that it attracts is weak. The electromagnetic field is weak. Things that are diamagnetic, that means that all of their electrons in their respective orbitals are paired with opposite spins, and therefore diamagnetic substances do not have a net magnetic field. So later on, we're going to talk about orbital diagrams, as I promised, and those orbital diagrams are going to be really important in helping to determine if a species is diamagnetic or paramagnetic. You'll need to do that on your homework. You'll need to probably have an exam question or so on that. But I wanted to introduce this topic now because we just got done talking about spin. Diamagnetic, those are species that have all paired electrons. Paramagnetic species, they have unpaired electrons. Paramagnetic and diamagnetic properties can be deduced from an orbital diagram that we will talk about later on in subsequent videos. So a few more things to talk about before we actually get to writing electron configurations and orbital diagrams. So now that we have these 4 quantum numbers that designate the space, the orbital of an electron, there are a few rules. We already learned one of them with the spin, is that they have to have opposite spins. That means that speaks to this principle called the Pauli exclusion principle. One way to say the Pauli exclusion principle is that the spins for an electron in the same orbital must have opposite spins, but another way to say that is that no 2 electrons in the same atom can have the same energy. So that means that no 2 electrons in an element can have the same set of quantum numbers. Okay? So that's why electrons in the same orbital have to have opposite spins, either the +1/2 or the -1/2. That rule, which we will use when doing orbital diagrams, is called the Pauli exclusion principle. And then the next rule that you need, or a concept to keep in your mind when doing orbital diagrams, is about the orbital's energies, or how do we know when to place a particular electron in one orbital versus another? Well, it depends upon the energy of the orbital that you are placing the electron in. Because as you know that we have different orbitals, S, P, D, and F, with different quantum numbers, those orbitals have different energies associated with them. The energies of those orbitals are dependent upon the principal quantum number and the azimuth law, the angular momentum quantum number. And you see that in general, as N and L increase, the orbital energy increases. You see, there's a little bit of a blip with the D's. We will talk about those later on. But the fact that orbital energies are different is going to help us determine when we place an electron in a particular orbital. So I kind of have this graph here, or this plot here, to show you the different energy orbitals. We're going to find out that orbitals that are of lower energy are filled first, and we'll be able to determine what those orbitals are from the periodic table as a guide for us. So those are some concepts about orbital energies, about the Pauli exclusion principle, and the spin quantum number that we need to have in place before we finally get to being able to write electron configurations for elements. Now, this is where I'll stop this little vignette, and this is where we'll begin the next video.